Hello and welcome to our 11th session. In this session we're going to be starting off with some thoughts on the density of states. Then we'll go into this idea that material equilibrium requires that the Fermi level be straight and horizontal. And there's two ways we're going to look at that. First, the Einstein relationship between something called the diffusion coefficient, which we haven't defined, but we will in just a little bit, and the mobility mu will show that if indeed the Fermi level is straight and horizontal, we have material equilibrium. Material equilibrium implies there's no net current, zero current, no charge motion. And then we will start to tackle one of the most important equations that we'll be using both for the p-n junction and for the bipolar junction transistor, and that is the minority carrier diffusion equation. Lots to do, but first let's listen to a wonderful performance of Rondo alla Turca by Wolfgang Amadeus Mozart in a, well, let's say non-conventional performance and arrangement by Greg Anderson and Elizabeth Rowe. So we'll see you in a few minutes. Okay, so let's jump right in. And the material for today's discussion will be mostly from chapters 4, 5, and 7. Chapter 6 is work problems, and you can go through those and hopefully get something out of that. The main topic for today, it's a relatively challenging topic, is the minority carrier diffusion equation. But first, let's talk about a little bit about the density of states. And the idea is here that we want to know how are electrons distributed in the conduction band. Here's the conduction band, and we want to know where are the electrons, just like we wanted to know how are the air molecules distributed in a balloon, the Maxwell-Boltzmann distribution. We found there that there were no air molecules that had velocity of 0, which is kind of a non-intuitive result, but that's what the math tells us, and that indeed is correct. Here we find that there are no electrons at the conduction band edge, and we can see that by looking at the density of states functions, which shows that if E, and E is this energy above the conduction band edge, if E is equal to E sub c, then there are no states. The density of states is precisely 0. Now, what are the density of states? Well, I like to compare this to mailboxes and letters. The mailboxes would be the density of states, and the letters would be the particles. In order to have a letter in a mailbox, first you have to have the mailbox. You have to have a state there. And, of course, if you want to find out how many letters are in how many mailboxes, we multiply the number of mailboxes by the probability that a letter will be in that mailbox. If you want to find out how many states are in a particular energy level, we multiply the probability of the particle having that energy level with the number of energy levels that exist at that particular point in energy. And it's going to work out, if we follow through the theory is not, we're not going to go through the theory here. It is developed in section 5.6, and you can go through and we get this result. The interesting thing about the result is that it is square root function of the energy above E sub c. So the number of states increases with the square root, and yet the energy decreases parabolically, because at the conduction band edge, that's just enough energy to kick the electron up and have it sitting at the energy band edge with no kinetic energy at all, and that is essentially impossible. There must be some kinetic energy. So we find, if we go through all the mathematics, and I believe that's one of the problems which is worked out, that the maximum number of electrons is sitting up kT above the conduction band edge, which is, as we know, is 0.026 electron volts above. So it's somewhere in this region right in here. That's the maximum number of electrons. So there's none at the edge. There's the maximum number at 0.026 eV above the conduction band edge, and then the number decreases rather dramatically. Okay, so the next topic is diffusion current, and I'm going to motivate that by going back to the hot plate experiment, hopefully for the last time. I just remind you of how this thing works. Here it sits. We have N-type silicon. We keep one end of it at an elevated temperature so that the Fermi level is close to intrinsic on the right side, and the left side is clamped at room temperature, so that if it's N-type silicon, we have the maximum number of electrons here in the conduction band and the minimum number at the right edge. And that's indicated here. Lots of electrons where the Fermi level is close to EC, few electrons where the Fermi level is far from EC. So we are tempted to draw the diagram, the energy band diagram, in this form. And what we said was, if there's a lot here and there's a little bit here, what's going to happen? There's going to be a flow. There's going to be a flow of electrons from high occupancy to low occupancy. So there's going to be a movement of electrons from the left to right. But then we ask the question, what happens when they get over here? Well, there's no place to go. Not only that, since the temperature here is about 300 or 400 degrees Celsius, this is maintained at a low number of electrons in the conduction band. So this cannot be right. So let's put a big cross through that, big X through that. That is the wrong energy demand diagram. So when we've exhausted all the possibilities of what can't happen, let's try something that is a little different. In this case, the Fermi level is horizontal and straight, and the conduction band, and of course the intrinsic level and the valence band edge all bend up. They all bend up. Why do they all bend up to the same extent? Because they must be parallel. This distance here must be equal to this distance here, because the distance, in this case, energy band gap divided by 2, is a function only of the material. So E sub I and E sub C are parallel. If E sub C is tilted this way, then E sub I is tilted in the same exact manner. And now we've identified the x-axis with position. This is the left side, and this is the right side. Okay, so to examine this a little bit further, let's go to the conduction band itself. And the conduction band is indicated here. It works out that if the energy is low, I shouldn't say it works out, it is true that if the energy is lower, that's the electron energy is lower, that's positive. If the electron energy is higher, that's negative. The electric field goes from positive to negative. So the electric field is an arrow pointing from left to right, which means that a positive charge would be repelled from the positive terminal and be attracted to the negative terminal. Electrons, on the other hand, go opposite to holes. Electrons would want to go driftwise from right to left. However, there are more electrons on the left side than there are on the right side. So diffusion-wise, the electrons would want to go from left to right. So we have drift current from right to left. We have diffusion current from left to right. If they cancel out, we have no current, which is exactly what happens, and that is indicated by the fact that the Fermi level is straight and horizontal. There is no material motion. There is no net charge motion. There's a tendency for electrons to want to go from left to right. As far as diffusion goes, there is a tendency for electrons to want to go from right to left because of the electric field. Okay, so that's the basic idea. Now we can take a look in a little bit more detail at the diffusion current. The diffusion current says that the motion of charge, whether it's electrons or holes, always goes from places where there is more of them to places where there is less of them. So it's dependent upon the spatial derivative of the number of charges with respect to position. So in this case, well, I probably should have said J differential for electrons, because I have the N here. To make the units come out right, well, since it's a current, we must have charge. And what are the units of current density, which is what J is? It is charge divided by time divided by area. So the units of J are amps per square centimeter, coulombs per second per square centimeter. And therefore, I have coulombs per second per square centimeter on this term here, the dN dx, is coulombs per cubic centimeter, because N is a volume density, divided by centimeters. So it's coulomb, this term here, dN dx, is coulombs per cubic centimeter divided by centimeter, which is coulombs per centimeter to the fourth power. And therefore the units of d sub n are, pull this stuff all over here, I get centimeters squared per second. So just a couple of comments here. The diffusion current depends only, I should perhaps italicize that, only on the concentration gradient. So if we have more electrons on the left than the right, electrons flow from left to right. If we have more holes on the left side compared to the right side, the holes will flow from left to right. It does not depend on the direction or the magnitude of the electric field. The other thing is, which is equally important, is that we can have a large diffusion current even if we have a small number of absolute charges, because the diffusion current depends only on the gradient, the differences between. So if I have a little bit on the left and a little bit less on the right, I'm still going to have a reasonable diffusion current. That's not the case with drift current. Drift current depends on the absolute number of charges, electrons or holes. So we can summarize that here. For drift current, which is on the left side, we have NQV, and V is equal to the mobility times the electric field. And on the right side, it looks very different. Diffusion current is equal to the charge times this new constant which we've introduced, the diffusion constant multiplied by the gradient. And that's indicated by the table here, the summary of drift and diffusion current, and hopefully that all makes sense given what we've just been discussing. Okay, so the Einstein relationship develops a formulation between the diffusion constant D, which is relevant, I should say, for diffusion current, and the mobility mu, which is relevant for drift current. You would think that these are both completely non-related. However, in equilibrium, when the Fermi level is straight and horizontal, they do have a very important relationship, and that is called the Einstein relationship. So to develop that, we consider the number of electrons in the conduction band referenced to the number or the effective density of state at the conduction band edge. And we know that here the Fermi level for n-type is below E sub c. So this number is negative and relatively large. And we can differentiate that with respect to x. Why do we differentiate with respect to x? Because the conduction band edge is sloped. It has a slope. So dE sub c dx is going to be not zero. So if we do that using the simple rules of differentiation, we get equation 7.10. The 7 refers to the fact that it's in chapter 7. And we know that the slope of the band edge is proportional to the electric field. The bigger the slope, the bigger the electric field. In fact, it's equal to the electron charge multiplied by the electric field. So we put that into the expression here. We get equation 7.12. Now, at equilibrium, the drift current, we're going to claim, plus the diffusion current, if I add them up, I get a nice round number, namely 0. There is no net current. So drift current, diffusion current, add them up, and I get 0. And the minus sign here is because the drift current and the diffusion current always are in opposite directions. So I kind of jumped ahead a little bit, and without going through all that rigmarole to prove that, we kind of assume that, and that indeed is the correct expression. I substitute in an expression for the drift current to get equations 7.14, and then I just equate them. This term is equal to that term, and this is the Einstein relationship. And it's actually relatively straightforward to remember because there's a nice rhyme to it. It sounds nice. D over mu is KT over Q. So that's the way we remember that. And if you don't want to do that, and I hope you don't want to go through all this rigmarole, this fancy math, but you can also prove it by using units, and that is a very powerful technique. Okay, so in the last section we said that if the current is 0, net current is 0. By the way, we could have done this for holes as well as for electrons. We get the same exact result. If the current is 0, then the Einstein relation holds. But we didn't say anything about the Fermi level. So in this section, and I'm not going to go through all the math because time constraints, but here the issue is we assume that the current is 0, and we assume that the Einstein relationship holds. And if we make those two assumptions, then we get, and we go through the math, and it's a little bit icky, but for want of a better word, it really is quite logical, and the result is equation 723, and this gives the slope of, could be the conduction band edge or the valence band edge or the intrinsic edge, doesn't matter, all the same slopes. The slope of the intrinsic with respect to position, and here is the expression on the right side. Clearly the first term here cancels with the first term here, and we are left with this term must be 0. Immediately from here, because of the cancellation of these two terms, we get that d e sub f dx is 0, which requires, implies, means the same thing as the Fermi level is horizontal. So that's another important result. The Einstein relationship plus net current equals 0 requires that the Fermi level is horizontal. And the converse is just as true. If the Fermi level is horizontal and straight, then the Einstein relationship holds and the net current is 0. Okay, so our next subject is kind of important, and it is the minority carrier diffusion equation. Why minority and why diffusion? Well, whenever we see diffusion, we probably are going to have minority. Minority carriers are always associated with diffusion. Majority carriers are generally, I would say almost always, I don't want to stick my neck out too far, but I would say almost always associated with drift current. Okay, this is one of the most important theories and equations that we'll be using quite extensively in the p-n junction and the bipolar junction transistor. So let's start off by motivating this by considering a slab of silicon. We'll start with a very small width, the x, although this can be bigger, and I'll just mention that briefly in a few minutes. We have charge coming in, represented by the red arrows, a charge density per unit area, charge per unit area, or amps per square meter coming in, and generally we would assume that what comes in must come out. So Jn of x, and we're going to assume that this is negative electrons coming in on the left side, so that the electrons coming in all go out, and that makes sense. We're not destroying matter, or we're not creating matter, so it stands to reason that J of n of x is equal to J of n of x plus dx. In comes out. Is that always true? Well, no. And that seems completely non-intuitive, and I'm going to try to motivate why that may not be true. Well, it's not true if I create electrons in the slab. Then more electrons go out than come in. It's also not true if electrons are destroyed in the slab. More electrons come in than go out. Now, how can I create electrons in this slab? Well, I can shine light on it. That's one way to do it, and that's a reasonably good thing to do. I would create electrons in the slab here, and I'd have more electrons coming out than going in. Conversely, if I don't have light shining, I should say light shining and absorbed, because that's important, light has to be absorbed to create the electron hole pairs. However, I just inject electrons into the left side of the slab, and some of those electrons recombine with holes in the slab. They get destroyed. It's like matter and antimatter. I think there was a Dan Brown novel about that, made into a movie. Was it called Demons and Devils, I think, or something, or Angels and Demons, I don't know, something like that, where you had antimatter and matter, and they collided, and you had a big explosion. Well, fortunately, we don't have an explosion. However, we do have a situation where if I inject electrons into a p-type material, the slab, in this case, would be considered p-type, I can have electrons combining with holes. Now, the rationale, and we'll talk much more about this when we talk about p-n junctions and bipolar junction transistors, the electrons, let's say this is an n-type material, so I've got lots of electrons, and some of those electrons are injected into the p-type material. Well, in the p-type material, electrons are in the minority. It's like here they're in friendly atmosphere. They got lots of backup and support, friends. Well, here they're in enemy territory. Lots of holes, not too many electrons. Those holes are apt to combine with electrons, so I get many electrons less coming, or not many, but less electrons coming out than I have coming in. So in that case, the amount of stuff coming out is not equal to the first term. I have to add a term of how much stuff gets either created or destroyed. So now it's a little bit just of algebra. Instead of the J, what are the units of J? It is coulombs per time, and then per area, so I multiply by the area. What are the units here on the left side? The units of N are numbers per cubic centimeter. A dx are cubic centimeter, so that cancels out. Q, N, that's the total amount of charge, and of course its current is charge per second, so I have a time on the denominator. Okay, and this term is quite interesting. This term here we basically stick in. It says that the number of charges, and we'll talk about delta n in just a little bit, that is destroyed. That's why this is a negative sign here. The number of charge that is destroyed, again, the units work out to be exactly the same. It is this is delta n times a dx. Q is charge, and per unit time, the number of charges that are destroyed, the number of coulombs that are destroyed, is given by this term. This is a really important term. So we look at the basically it's just algebra from this time on. So canceling terms here, the a cancels and the q's cancel here. So this equation follows immediately, and we continue by adding the light term. This is destructive. That's why it has a minus sign. The number of charges goes down. Here, the number of charges will go up because light is absorbed. Now, what we're saying here is that n, the total number of charge in the slab, is equal to some equilibrium number plus an excess number. Now, so what is the equilibrium number of electrons in the p slab? If it's, for example, doped to 10 to the 16th, we would have 10 to the 4th. But there's more. The issue is that not only do we have the equilibrium number of holes in the slab, we have an excess. So if I put in 10 to the 18th, I've got 10 to the 4th plus a huge number, 10 to the 12th, 10 to the 13th, whatever it is, huge number of excess electrons in the slab. So that's more than a deviation. It's a big deal. And then we put that number into the left side, into the diffusion equation. So this is just a diffusion equation where now n is equal to the equilibrium value plus the delta n. Of course, the derivative of a constant with respect to anything, either time or position, is 0. So we have that the diffusion current is equal to Q times the diffusion coefficient multiplied by d delta n dx. So going back to here, we just stick that in with the first term on the right side, which is a first derivative of the current. We then take the derivative here, which gives us a second derivative of the excess charge density right here. And this basically is it. This is the minority carrier diffusion equation. It's either for electrons or for holes. Now, if it's for electrons, this kind of is generic, but I probably should have made it a little more specific by saying this would be a P here. Why do we put a P here? Because this is the excess electrons in the p-type, in a p-type material. They are a minority. Electrons in p-type material are a minority. Holes in n-type material are a minority. So to make equation 732 really more reasonable, it's best to put in the P here, which says that the electrons in the p-type material are a minority, and therefore the minority diffusion equation is the equation that holds. And here I just rearranged it by sticking the second derivative on the right side, or the left side, excuse me. And I made it into a nice color because this is a really important equation. When we deal with steady state, this term will be 0, so we'll just have 3 terms. When we deal with a situation without light, we just have 2 terms. This combination of the diffusion coefficient and the recombination time is called the diffusion length, and it has the units of length. And let's see, because the diffusion constant is centimeters squared per second, and of course the diffusion recombination time is in seconds. Take the square root, and it has the units of centimeter. So if tau is the time it takes to recombine, broadly speaking, dn times tau, or L sub n, is the length that a charge can exist in, for example, an electron, I should say, make it specific. An electron can exist in a p-type material before it's extinguished. It could be maybe 1/10 of a micron, or perhaps a micron, or whatever it is, but it's a very relatively small length. Okay, so a couple of special cases here. The first thing, for steady state conditions, the second term on the right side is 0, whereas this guy right here is 0. That's generally going to be the case, that this term will be 0. For a steady state condition and incident light with no spatial variation, if there's no spatial variation, then this term is 0. So what do we have left over? This term is always there, and you can't get away from it. This guy is he's ubiquitous. However, if we have no spatial variation, how would that be? Well, let's, for example, consider a slab going back here, and this would be a long slab in which we illuminate the slab with light uniformly from the left side to the right side. So there's no variation in position between the left and the right. And in that case, we would indeed have this term being 0, and we get a relatively straightforward equation. Delta N, the excess carrier concentration divided by the recombination time, is equal to the amount of light, and we'll talk a little bit, I think we have some problems about this, to get the units here. And what we have in this case is that the excess carrier concentration is equal to the light that comes in multiplied by tau. And that's important, because in that case we always have some recombination, because the light is on indefinitely. It can be on for a second, it can be on for a year. It's on until I turn it off. So there's always going to be recombination, and tau is generally in the order of nanoseconds. So there's a steady state condition where the amount of excess charge is not equal to the amount of light, but the amount of light multiplied by the recombination time. And this is kind of important, because you can imagine what we're talking about here is a solar cell, and that's a rather important equation. We want to make, for solar cells, we want to make tau as large as possible, and that is quite a challenge, quite frankly. Okay, now if the recombination time is large, very large, no incident light, and steady state conditions, whew, that's a lot of ifs. But no light, steady state, these two terms are 0. Tau big, then, well, it's there, but it's suppressed in this particular case. Then we have this first term is approximately equal to 0. And what that says is that the slope of delta n over dx is approximately constant. If the second derivative is 0, the first derivative is constant, which implies that the current is constant, because the current, it must be someplace here, the current is proportional to the first derivative of delta n with respect to x. So the current is constant, but not, and this is a big deal, not delta n. Delta n is linear. If the first derivative is constant, then the argument of the first derivative must be linear. So what it means is that the excess carrier concentration changes. In fact, it's going to decrease generally. Does it have to decrease? Depends on the boundary condition. It depends on what happens at the two ends. In a bipolar junction transistor, we require that the excess carrier concentration be zero here. So we have lots coming in, we have zero coming out, and therefore the variation is a straight line from the in to the out. If, however, it's free running and I have no requirements on the right side, it is possible that the excess carrier concentration coming in will be equal to the excess carrier concentration going out. Not a very useful device, by the way. Extremely not useful device, because the current in that case is, well, we'll talk about it. We'll talk about it when we talk about bipolar junction transistors. But a straight horizontal line is a line, so that's possible too. Okay. Okay, so there's a couple of examples that are relatively straightforward. I generally like to put in the not so complicated examples that you can read over, and hopefully these are not be too difficult to follow. So let's skip now to the last part. We have a final video clip. This is from the really wonderful movie called Flashdance. I believe it was 1983 or 1984. And I'll just give you a little bit of background on the movie if you're not familiar. The movie concerns a young woman played by Jennifer Beal. Her name, I believe, is Alex. And Alex is born on the wrong side of the tracks. In the day, she works as a welder in a steel factory in Pittsburgh, and by night, she is an exotic dancer. But her dream, her passion, is to dance in the ballet. And she goes through a lot of machinations. That's what the movie's all about. But finally, at the end of the movie, she gets a chance to audition to an exclusive ballet school in the exclusive section of Pittsburgh. She is not at home by any means, and she's very nervous, and she has to convince this rather skeptical committee to accept her. And having been on PhD committees, I know that that's a very tense time. Students are trying to convince us that he or she is worthy of getting her degree. So here she is. She's trying to convince them, and take your passion and make it happen. Flashdance. What a feeling. And we'll see you next time.
slow glowing dream that your fear seems to hide deep inside your mind. All alone I have cried silent tears full of pride in a world made of steel.